Okay, so today we are going to deal with isometries. At least I would say we keep going with isometries in the upper half plane model. And then we will move to the second model in the disk. And already after that, we're studying higher dimensional models, okay? I actually, I probably confused you a little bit with elementary transformations. I mean, Möbius transforms, since I mentioned, so generally, if I am taking Z to AZ plus B over CZ plus D, right? And I was actually talking about first, I was talking about ABCD being complex numbers. And then indeed, any such F, right? Any such F is generated by those, right? A Z or Z shift to Z plus A. In particular, it includes those rotations Z to Z multiplied by the complex number with the absolute value 1. And also, what else? Also, I need to include this, right? But these guys generate the subgroup PSL to C. But this is about, so this is kind of a remark, okay, about the group PSL to C, which is the automorphism group of the Riemann sphere C bar, which is C compactified with one ideal point, right? This is my C bar. But right now, right, but we work currently with the group PSL to R, sorry, PSL to R. And I already showed that this is the subgroup. So this is our conformal automorphism group of the upper half plane. And this is the subgroup of isometry group of, actually orientation preserving isometry group of the H2. Well, where I mean definitely isometries of my upper half plane, right, with respect to this metric. So here we consider the pair U2 with GU, where GU is just the Euclidean metric tensor divided by y squared, right? And my line Z is xy, and y is positive. Okay, so in fact, the isometries that are, one can notice that actually any isometry here, right? So we have isometries of this type, where A, B, C, D are real. And elementary transformations are elementary transforms are those, right? Are z to lambda z, where lambda is positive. Another type is shift with respect to any real number. I forgot I denoted it by alpha or a. It doesn't matter, I guess. So it's r, and I also need to consider -1 over z here, right? And yeah, since I want to preserve the upper half plane. Okay, now so again, yeah, these three they generate PSL to R, right? They generate PSL to R, and one can notice, so, and one can notice that all these are orientation preserving isometries. So one can notice that all these guys are orientation preserving isometries. So let me, I don't know, denote them by 1, 2, 3, right? All this 1, 2, from 1 to 3 are from isome plus H2. Okay, the second comment is that, let's continue. We notice that, so we also discussed reflections, right? So we also discussed hyperbolic reflections. So I'm writing here hyperbolic, but from now on, I assume I will omit this word. So we are talking about hyperbolic reflections. And if it is Euclidean, I will specify it. So we also discuss reflections are L, right, in geodesics. So far in geodesics, L in H2. In the sense of Euclidean geometry, this is either the Euclidean reflection with respect to, so this is my geodesic L, right? So this is, suppose it is O, right? So an example is the geodesic. Okay, let me denote it by indeed L. So in this picture, it is L of Z. It is just minus Z conjugate, right? Minus the conjugate of Z. This is the Euclidean reflection. And other reflections are, so for any vertical line, it is Euclidean reflection, and if if a line is, okay, so these are Euclidean reflections with respect to vertical half lines. Or inversions, which I will denote by I sub omega, where omega is a circle. Or if it is important, I will specify that this is omega centered at the point A and with the Euclidean radius R, right? So the length. So this is the point A plus R, obviously. Okay. So I will also write that I will sometimes use this notation I sub A comma R. Okay. So inversions, right, with respect to circles that are orthogonal to the boundary. Okay, to the axis y is equal to 0. Okay, so these are orientation. So it's kind of like it's kind of an obvious fact, but still let's emphasize that. Reflections RL are definitely isometries, and they are orientation reversing isometries. So they belong to the group isom H2 minus isom plus H2, and I can denote this. Well, I'm not going to use this since they do not form a group, right? I'm not going to use this notation like isom minus H2. What one can denote it as isom minus H2, but like these do not form a group. So in order not to like create more confusing notations, I will avoid it. So this is the set of, I will just write the set of orientation reversing isometries. Orientation reversing isometries. Okay, so as a like consequence of all of this, right? We have the following. We already proved that PSL2R is the subgroup of isom plus H2, and we also show that reflections like also belong there. So like the idea is that by adding isometry, so taking PSL2R plus all reflections, we already get everything, right? We already get everything. Moreover, there is the following consideration. One can take, in fact, for any isometry. So suppose you have some isometry, right? I will not write it down for now, but suppose you have an isometry moving, like somehow moving the points in the plane. And suppose you find a point Z, which is the image of I, right? On the other hand, you can find a reflection such that which sends I to any like given point Z. You just need to take a geodesic passing those points and find an orthogonal geodesic here, and to make a reflection, this will be a bisector of this segment, right? And the remaining geodesic, so if your initial geodesic was, sorry, if your initial isometry was orientation reversing, then you will kind of decompose it into reflection and obviously something orientation preserving. And we basically want to show that here we actually have an equality. right? So the goal is to show that there is an inequality. But right now, what do we have as a consequence of all of that? We have that the group generated by, okay, the group generated by isometry, by an isometry, sorry, by this orientation reversing reflection, right? And its semi-direct product with PSL to R. So I'm taking this element minus Z conjugate, minus conjugate of Z, and I'm taking this semi-direct product with PSL to R. We already show that this is the subgroup of the full isometry group, H2. And our goal, right, or claim, right, show that this is, we have here that this is actually inequality, right? So it is equality. Here, they should coincide. Another interesting remark about reflections. Actually, one can show that reflections, like the subgroup of all reflections, form a normal subgroup. One can notice that if you conjugate a reflection, so another interesting lemma, that the conjugation, let gamma be in atom H2, RL any reflection, then gamma RL gamma inverse is also a reflection, and moreover this is a reflection with respect to the geodesic gamma of L. Yeah, but right now we are not going to use this while we are. So in fact, if you add one reflection, you can kind of then get anything else, right, by using orientation preserving isometries. So, okay, but we are going to mention, like we are going to discuss it a bit later. So what is important right now for us? Yeah, right. We also discussed pairs of geodesics. And their like relative, I don't know, relative position of pairs of geodesics, right? So let me just remind the following, the picture. So we can have the following types of relative position. Let it be one line, the second line, L1, L2. Then here is the tangent semicircle. This is going to be L3. And there will be another. Okay. Do I need it? Yeah, let me take it. So I wanted to take also a geodesic L4. So there are three types, right? L2 intersects L4, right? Sorry, L2 intersects L4. So its intersection is non-empty in U2 or in H2. The same is true for L3 and L4, right? L3 and L4. Also, this intersection is non-empty, so they intersect. Also, we have the following. L1 is parallel to L2. And L2 is actually parallel to L3, right? L2 is parallel to L3. So we call it parallel, means meet at infinity, right? Meet, okay, I will say at the boundary, at a boundary point, right? At a boundary point. Important remark. It doesn't follow like the above doesn't, okay, it doesn't imply that. So if L1 is parallel to L2 and L2 is parallel to L3, that L1 is parallel to L3. This is, so they can meet pairwise, but in different infinite points. That's why I wanted to give you this picture, since L1 and say, okay, yes, L1 and L3 diverge. Or are disjoint, are divergent, disjoint. This means they do not intersect even on the boundary, right? In this case, the same is actually true for L1 and L4, right? So here, see below, I will just write a comment, say below, and L2 and, sorry, L1 and L4. L1 and L4 diverge too, right? In this case, we have a common orthogeodesic. So for example, in this case, there exists a common geodesic. Realizing the distance between two lines, right? So say for L1 and L4, right? There is a geodesic L such that L is orthogonal to L1 and L is orthogonal to L2. And obviously its geodesic segment between two lines realizes the distance, right? Okay. I also didn't say something about angles. I'm writing here angles, but another very important observation, since our metric, hyperbolic metric in the upper half plane is just the Euclidean metric scaled by something, we have this so-called conformal behavior here. In particular, this implies that the hyperbolic angles between geodesics coincide with the Euclidean angles between the associated curves in our upper half plane model. And actually, I wanted to. So here, right, angles. Angles, hyperbolic angles coincide the following lemma. Hyperbolic angles coincide in U2 with Euclidean angles. I think let me move to the next board. So, right, examples. Are here. We can take upper half plane model. Let me take the vertical geodesic passing through 0. And also I'm taking, say, the unit. Let it be L, right? Okay, L1. And the geodesic passing through this. So it's a semicircle orthogonal to the boundary. The angle here is pi over 2, right? Angle between L1 and L2 is pi over 2. Since, okay, the angle between curves is just by definition the angle between the corresponding tangent vectors to those curves at this point. Okay, and this is in particular why this model is very nice. You can really draw triangles with some nice angles, and it allows you to basically make Euclidean constructions in the upper half plane based on your hyperbolic data, right? So for example, I can add another geodesic for the question, like, okay, let it be example number 2, since this picture, okay, I want to make it a bit, so, right? This is my vertical line. If I want to make example 1, right? This is example 2. Find so this is L1, this is geodesic L2. So the question, find L3 such that the angle between L3 and L2 is some certain angle alpha. What would you do here? This means that the tangent, right? This means that the tangent line to this semicircle at this point should give you the angle alpha with your vertical line. Yeah, this is actually the first observation. I can take, I can find another, I can try to find a semicircle also making the angle alpha at this point, but I can do it in a bit different way. I'm going to find like a point located on this arc such that the vertical line through this point gives me the angle, an angle alpha. right? But from Euclidean geometry, we know that the radius to this tangent point gives always the angle pi over 2 with the tangent line, right? In particular, this implies that I can continue this geodesic here. This implies that this angle is pi over 2 minus alpha, and thus this angle is also alpha. So what does it remain? It's just to find an angle alpha here, and this gives me the triangle pi over 2 alpha, and the third angle is 0. So we already kind of we are coming to triangles. It is allowed to take triangles with vertices at infinity. So triangles and actually just any polygons here, right? Polygons. I'm going to discuss only convex polygons. So, but generally, like triangles are just the shapes bounded by 3 geodesic segments, right? So triangles is just the convex hull of 3 points, or you can think of given A, B, C in H2, we just find geodesics, and this gives me the triangle, right? As for polygons, if I'm thinking about convex polygons, I will just take either again the convex hull of some finitely many points in the plane, or one can take an intersection of finitely many half planes, and so generally I can intersect finitely many half planes. So I'm taking by k from 1 to some n, and I will just denote it by lk minus, it is a half plane where, let me draw a picture. Suppose it's goes like that. So this is my P, right? And this means that my geodesics, my half planes were oriented in such a way that this was L1, that it be L2, L3, and L4, right? And here, this P, it kind of means that here we have plus, right? While everything corresponding to the interior of this P is oriented as negative. So I'm, in particular, this means that in this picture, my L minus was here, and my half plane L plus was on the right side. No, actually the opposite, right? My L plus for this vertical geodesic was here. My L minus, the entire half plane was on the right side. And finite intersections with non-empty interior, we always assume that the interior of P is non-empty, right? it gives me some convex polygons here. It is easier to describe when you have just 3 points or 3 sides. And what is interesting about triangles? It is interesting that actually triangles are uniquely determined by their angles. Okay, before going into, before delving into triangles, let me also remind something about the behavior of geodesics. I actually draw this picture and I wanted to say something. The huge difference between hyperbolic geometry and Euclidean geometry. So let me leave a remark just here. What is the difference? Another difference between hyperbolic and Euclidean geometry. Hyperbolic and Euclidean geometries. It is this picture. I can, so let it be my upper half plane. Suppose I have a geodesic, one geodesic here, the vertical one, and I have a point in the Euclidean space. We will have precisely one geodesic passing through this point and not intersecting our line. So the point doesn't belong to this line, okay? In hyperbolic geometry, we have infinitely many such lines, right? So we can start from, I can basically do a lot of things. I can take this geodesic, right, the vertical line passing through this point. It does not intersect inside of the hyperbolic plane. And I can also take more. I can take the, sorry, it goes wrong. So I can take the semicircle, which is tangent to my geodesic L here, and also passes through this point. So technically, right, this L1 and this is L2. Technically, both L1 and L2 do not intersect L inside the hyperbolic plane. And then I can take infinitely many, like there is this like the whole, like I would say, like the sheaf of lines passing through this point. I have infinitely many geodesics. And all this, right, all these geodesics, they go through this fixed point A such that, and do not intersect L, right? This is the huge difference between hyperbolic and Euclidean geometries. And again, I remarked that if one is the first line is parallel to the second and the second is parallel to the third, it doesn't imply that the first is parallel to the third. While in Euclidean geometry, it would, right? It would imply this. Okay. Also, in Euclidean geometry, you can you have a large group of similarities. You can just scale triangles. It doesn't change angles, but changes on the distances. Here, it's not true. And already in this picture, I'm giving you an exercise here. Exercise. Show that, so suppose this is, okay, this is my point I. Okay, I can I assume this is a unit circle, and let this point be, I don't know how to, let it be A. So in this picture, show that the hyperbolic cosine of distance between the point I and A is equal to 1 over, okay, if I'm not mistaken, it should be 1 over sine alpha. Or cosine, but I think it is sine. And yeah, you just can, there are two different, I think actually there are two different hints to this exercise. You can either parameterize the semicircle and just integrate using the metric GU, right? Or you can rotate this. You can find an appropriate Möbius transformation, which sends the semicircle to the vertical line such that I is fixed. So you need this rotation. And you will find the image of this point here, and then you will compute the distance. We'll already have the formula for, right? We already have the full formula for the distance between two points on the vertical line. And yeah, this will be fine. Okay, so and what does it mean actually? We have a triangle, right? We have a triangle with angles. So in the triangle, there is a corollary of this. Corollary. In the triangle, with angles, pi over 2, alpha, 0, everything is parameterized with respect to alpha, right? Metric in the triangle with such angles, the metric quantities depend only on alpha. Depend only on the angle alpha, right? This is actually important. All right. Now, yes, I have a few minutes before the break. I want to remind again about the types of isometries. So so our goal was types of isometries. I forgot to say again, it is related to the discussion in the beginning, since we introduced that there are 3 types of isometries, right? By the way, so recall that H2, the compactified H2 is H2 with this ideal boundary, where the ideal boundary of H2 is the line y is equal to 0 and the infinite point. It is actually, so we have like the infinite point and the line, right? It is actually homeomorphic to the circle S1, right? And to see this, you use the stereographic projection. So So this is just R1, right? I will write here that this is basically R1 with the infinite point, right? And this is, using the stereographic projection, homeomorphic to the circle, to the unit circle. Okay, now the following three types. Again, we have elliptic isometries, These are those, so F is an isometry from H2 to H2, right? And in fact, it can be extended to a homeomorphism of the compactified space, right? So in isometry, then it is elliptic isometry. I would write elliptic isometry if the fixed point set of the isometry F in H2 is non-empty, right? Is not trivial. And the elements that belong to those type are obviously reflections, where the fixed point set of RL is precisely L, right? Or say rotations with respect to the point A and angle theta. So definitely the fixed point set of this rotation with respect to A and theta is precisely the point A, right? Hyperbolic rotations. And a typical example of a rotation, let me suggest the following example. So let it be I. Right, and I want to take a rotation with respect to I and angle at angle phi. This is an rotation preserving isometry. And in fact, that isometry I mentioned somewhere here, -1/z, right? It is precisely the rotation, -1/z. Yeah. There is an interesting remark about reflections, but I think we will start doing this after the break. If I take, so let it be L, right? Let it be L. And this this is my, okay, suppose it is omega, right? Then actually this rotation is a composition of two, okay, reflections. It is the composition of the reflection RL with the reflection with respect to geodesic omega. Well, it's not good actually notation, since I usually mean the Euclidean nature of this object. So it's better to use like another L, I don't know, prime or something. But this here I mean hyperbolic reflections, definitely. So a composition of two hyperbolic reflections intersecting at some point gives you obviously a rotation. And in this precisely case, this is this rotation. And in fact, this inversion in the unit circle can be described in terms of 1/z bar. Yeah, but let's discuss this over after the break. And so the second part of the lecture is going to be devoted to inversions and to transition to the second model. Yeah. Okay, let's make a break. Okay, so we are back online, and let me remind a few like our goals. So one of the first goals is actually to find the full isometry group and to show that it is going to be eventually equal to the semi-direct product of PSL to R, its orientation preserving isometry group, and it's enough just to take one reflection. Like the idea is that probably it is possible to make it in this model, but I'm not even sure how. And in any case, it turns out that it is easier to prove this using another model. There are a few other facts that are easier to show using other models of the hyperbolic space. And one of those facts I already mentioned here, that in triangles, all metric quantities like distances, well, basically like the lengths of size, the length of geodesic arcs from vertices, between vertices, they depend only on the angles. It is true for any geodesic triangle in hyperbolic plane, and it is a bit easier to show that using other models. One more remark I wanted to leave is the following. Actually, in the beginning of the lecture, I said that I left a few confusing comments in previous lectures, and one of the comments was about this rotation over here. This is not that rotation. In this case, so for example, this rotation, it is the rotation. Let me draw a picture, I think, on the right side. So in this case, it is a rotation just in the entire plane C. And this is going to be this rotation, right? So we rotate points Z goes to some Z, E, I, sorry, E, I, theta. So it is on the same circle, whose radius is absolute value of C, right? And it is just rotation around 0. If I make a shift, so it's if I'm writing here Z minus beta plus beta, it will be a rotation around any shifted point beta, right? Not with respect to the origin. It is still going to be actually an isometry in the hyperbolic space, but we will discuss it later. It's going to be the upper half space model for the hyperbolic three-dimensional space. And when we're talking about upper half-plane model of the two-dimensional hyperbolic space, we need our isometries to preserve the upper half plane. And definitely this is not that type of, and besides it has complex, right? It has complex, I would say complex parameters over here. So it will really be a group which is really bigger. Okay, now back to rotations. In fact, I want to leave the following, again, problem or proposition. Let me say that it is a proposition. So proposition. Yeah, by the way, I mentioned rotations and it's kind of intuitively clear, but in fact, the rotations should be clearly defined, right? So rotations, by definition, okay, I'm using blue, but probably it's better to use the orange guy. So by definition, right, by definition, rotation is an isometry defined by, it fixes the point, right? A, and on the other hand, it takes, so suppose your A, okay, suppose A is here. It is the point in the upper half plane, right? And then any other point P is rotated in such a way, right? So how to define formally. So I'm taking the geodesic, right? I'm taking a geodesic L, passing through P, and then I need to find another geodesic passing also through A, such that the angle, so L, the geodesic L is sent to L prime, such that L prime contains P, and the angle, the oriented angle between L and L prime is theta, right? And then P is sent to P prime such that the distance LP is equal to the distance LP prime. So, but again, there will be two options of choosing the image, right? And I want to make this I want to make everything counterclockwise, right? Well, it depends on the value of theta basically, but the rotation is so such that the angle is this, right? So it's like a counterclockwise rotation of a geodesic. Okay, a counterclockwise rotation of a geodesic L into geodesic L prime, right? And finally, the right for any P. So I didn't write it here. So and for any P, we do the following, right? For any P, we find this geodesic L passing through A and P, then rotate it counterclockwise, such that the angle here is theta. And then, okay, yeah, and then we find the point P prime. So the rotation A with respect to theta of P is P prime, such that the distance between AP and AP prime is the same. Yeah. So it belongs to the geodesic L prime, such that the distance between A and P is equal to the distance between A and P prime. Again, I'm not doing, I need to really follow the orientation. I need to follow the orientation considerations, since otherwise I would rotate with, I can choose another point P with the same distance on the geodesic L prime, but it will give me another angle, right? So that is, I'm choosing P prime in such a way that actually the oriented angle PA P prime is theta, right? So my oriented angle has to be theta. I will write down this here. Oriented angle P A P prime is theta. This is very important when we define, right? When we define rotations with respect to points. And the proposition, if L1 and L2 are geodesics in H2 such that say L1, L2 give me some angle alpha, so they intersect. The intersection is non-empty. Angle is some number alpha. Then the composition of reflections are okay. So here I'm going to write RL1 and RL2, meaning that we first, right? So what do? We take first reflection with respect to this line L2, and then with respect to this geodesic L1. So it's indeed the, okay, in this picture, this is the rotation with respect to the point A and the angle 2 alpha. This is the following, so the following statement is true. In particular, this means that all rotations, in fact, all rotations are generated by reflections. And because for any two, so if you fix a point in the hyperbolic plane, right, you take just two geodesics intersecting, meeting at this point. And if you have like a desired angle alpha, then you need to choose those geodesics, yeah, to be intersecting with angle alpha over 2, right? And the corresponding composition will give you the rotation with at angle alpha, okay? Yeah, so this is, yeah, this is what about rotations. And now I'm going to get back to inversions and reflections, as we are going to use them heavily. So now inversions with respect to circles and hyperbolic reflections. By definition, right, let me remind the definition. So let omega be a circle in R2 with center O and radius R. Okay, then this is omega. This is my radius R. So then any point X, for any point X, we find X prime. Is X prime. It belongs to the ray OX such that the Euclidean distance between OX and OX prime. So for the Euclidean distance, I will just write the norm OX times OX prime. The product of those two norms is equal to R squared. So for every point X, right, for every X, well, for every X, obviously not being equal to O, right? I omega of X is defined this way. In particular, and I omega of O, we seem to be an infinite point, and I omega of the infinite point is O. Obviously, the circle omega is fixed point-wise, right? So obviously, the fixed point set of I omega is the entire circle omega. One can write this actually in the following way. One can write that the vector, so I can rewrite this, is that the vector OX prime is equal to some lambda OX, right? Since definitely the vector OX prime is collinear with the vector OX. What is the coefficient? The coefficient is actually this one, since the scalar product, what is the norm? It is the square root of the scalar product of OX with itself, right? I can actually just write that this is equal to, I can change this with lambda OX. So it gives me lambda multiplied by the square, the scalar square of OX is R squared. So my lambda is just R squared over the norm of OX squared, correct? And so like the, okay, then again, as we discussed in the upper half plane modal, one can write that if this is a unit circle, this is I, this is 1, minus 1, right? And this is my omega. Then in this case, we have I omega of Z is minus, sorry, it is 1 over the conjugate of Z. Or I can rewrite it a little bit like Y, right? I can like, basically the question is Y. Sorry, not here, but here. Suppose this is your point Z. I need to find the point belonging to the same ray, right? But I can multiply this and this by Z, and this gives me Z over Z bar, and eventually this is equal to Z over the norm of Z squared, since Z times Z bar is precisely the square of the absolute value. So it is the absolute value of Z squared. Okay, that's good, since this is precisely what is just written here. The radius is equal to 1, right, of my omega in this example. Yeah. And the OX, its absolute value, I mean, its Euclidean norm is precisely the absolute value of the complex number z, since in this case, O is the origin. In the general case, it gives, I think it gives the formula. And the formula in the general case is here, so I'm going to, okay, yeah, I'm raising this, but we keep in mind that this is our goal to show, to understand the full isometry group of the hyperbolic plane. Let me- So, and I'm giving like a lemma, but it can be considered as an exercise. In general, right? In general, if O is some point AB, right? Then, okay, it is in R2, right? Then I omega of any point with coordinates xy is precisely this. It is AB plus the following. In fact, I'm just using precisely this. So I need to write that the image, right, x prime, so the vector, basically, if I write this minus this, it is my vector or x prime in coordinates. On the right side, so what I'm going to write here, I need to have r squared over this norm multiplied by the vector of x. So we're writing the fraction. Here I'm going to have r squared, right? And here I'm going to have the absolute value of the, well, the norm squared of the vector of x. But this is x minus a y. Okay, let me write it like xy minus ab, right? Norm squared. But you understand that this x minus a, this, okay, eventually you will have here x minus a squared plus y minus b squared, right? And this is, so this scaling factor is applied to the vector, obviously x minus a, y minus b, since this is the vector of x from the above board, okay? From the board above. Okay, then I'm going to, now I'm going to, yeah, so actually, I also wanted to leave you a formula for the distance, but right now it's not, probably it's not necessary. So, yeah, we are going to use it. I told you that there is another model, and now I suggest to consider the following picture. So eventually this is going to be a theorem. So take a picture. This is my upper plane. And this is 0, 1. So this is U2. Okay, this is my unit circle. This is minus I. This is I, and this is minus I, right? And the point is that I want to send the upper half plane into the unit disk. And it is also like a feature of inversions that if I want to send, in particular, I want to send the line, the horizontal line, I want to send it into the unit circle. So I want actually to find a circle such that the radical axis of these two circles is precisely this horizontal line. And this is this circle. It should be the circle centered at minus I and passing through. So I'm taking this omega here, blue one, centered at minus I, and passing through points 1 and minus 1. It is well known that the image, so in this picture, it is known, so the theorem, like part 1. Let me denote the unit circle as just S1. Okay. So let omega be omega centered at the point minus I with the radius apparently square root of 2, right? This is going to be the radius of omega. So this is center and this is radius. Then the following holds. The first part, the I omega of the horizontal line y is equal to 0. Okay, I would actually write it this way. The image of S1 is such a line. Okay, it is a Euclidean line being a radical axis. Okay, being the radical axis of circles omega and S1. Well, this is kind of a standard fact from Euclidean geometry, but in this case, it is precisely in our case. In our case, it is precisely the axis y equals 0. The radical axis is actually just the line that has the equal degree with respect to, and having equal degrees means that it is the point for all points on this radical axis, the product of Euclidean geodesic segments from the first. So you take any line, you take any Euclidean line intersecting, passing through X and intersecting your circle, and the product of these two segments is all the way the same for all lines through X and this circle, but it also should be the same. This number, right? This quantity should be the same for the second, and the set of all such points satisfying that the degrees are equal, it is well known to be a line. And if two circles intersect at 2 points, then this radical axis obviously passes through these intersecting points, since at those points the degrees are 0, right? The degrees are equal. The degrees of those 2 points are equal to 0, since one of the Euclidean segments is the segment of the length 0. So it can be checked by hands that this is true. And the second part of this theorem says that actually the upper, so I omega of, okay, I omega sends U2 to B2. So this the number, the set of all numbers shows that the absolute value is less than 1. That this thing is a homeomorphism. But okay, the question is it true? Yeah. Yes. So I'm taking all these points. If I want to consider compactified, I can take this with the boundary, right? And I can take the compactified U2 with both the horizontal line bounding the upper half plane and with the infinite point, right? But I will first write this. Is a homeomorphism, right? And in fact, it is a diffeomorphism. Is a diffeomorphism. Okay, I will just write diffeo. Okay, it is a diffeomorphism. This is very important. Okay. In fact, I can make it to be a homeomorphism even of the compactified spaces, but right now it's not so important. What is important for me is that now I want to equip the disk, right? So B2 is my disk. I'm already preparing you for higher dimensional notations that I'm going to use. So this B2 means that this is the two-dimensional ball, right, centered at the origin and having radius 1, okay? Right, now I'm going to finally make it to be a Riemannian isometry. Okay, yes, I also need to give a comment. So the first part is it is kind of a, yeah, like high school exercise in Euclidean geometry. The second part is already not probably high school, but it is still like an undergraduate exercise level, since everything is already actually written down. We wrote the inversions and coordinates. So you can check that this is a homeomorphism just by hands, right? Yeah, it's also a good exercise. Why not? Yeah, so on this board, I'm trying now to, I will give like a hint to this theorem. So now let G sub B be the Riemannian metric in the ball B2, defined as follows. So it is going to be DGE over, let me just check, it should be 4, I think. Yes, it should be 4 over 1 over, so I can, if we use the complex numbers interpretation, like the complex interpretation, I'm going to write that this is 4 over the norm, okay, over the 1 minus the absolute value of z squared and squared again. Or, which is like the same, it is the Euclidean metric tensor GE with the following. So it is 2 over, so it is 1 minus x squared minus y squared, and all this is squared, right? I hope it's correct and I'm not, yeah, that should be true. Okay, and yeah, so what do, again, so let GB be a Riemannian metric, right? I will actually write, since I already defined it as a Riemannian metric, so it is a Riemannian metric in the ball B2, right? Then, in fact, I omega from here gives us not just the diffeomorphism, it is a Riemannian isometry, right? Then IT from the pair U2 GU to the pair, the unit open ball B2 to this metric GB is a Riemannian isometry. Okay, I will just write the hint to proof. Write down this in coordinates. So I omega of xy, I rewrote it somewhere in my notes. So the first, you need to show that it is equal to 2x over, okay, let me just rewrite it. So it is the pair of the following fractions. The first is 2x over x squared plus y plus 1 squared. The second coordinate is 1 minus x squared minus y squared over x squared plus, again, y plus 1 squared. I suggest writing that this is a pair. I didn't know, we can denote this by, I don't know, x1, y1, and then I just suggest you rewriting the metric tensor. So then in terms of, right, xy, sorry, x1, y1 from B2 GB, right, GB is basically this. It is g x1 squared plus g y1 squared multiplied by 4 and divided by 1 minus x1 squared minus y1 squared squared. And yeah, what I just suggest to do is to plug in, it kind of remains to plug in. So this is my x1, right? Okay, let me use the color. X1, y1, right? It remains to plug in x1, y1 as functions of x and y, and see that you will eventually get gu of xy, right? So it will be kind of GB computed in the point. Okay, it remains. It is actually not, technically, it will not be very easy. It remains to plug in x1 of xy and y1 of xy, and see that, okay, and see that GB, like computed at the point with coordinates x1, y1, right, is going to be equal to the tensor GU computed at the pair xy, right? And this will be the end of proof. It is not, I don't know, it's just like, you would probably spend the letter size page of like just computations by writing this down. There is a bit another way you can write down the length of the curve of a hyperbolic geodesic defined with respect to this metric, and then check that the length of curve in this model and will be equal to the length of the curve with respect to this model, where one curve is the image of another curve. And it will basically give you this fact about isometries. Okay, so for example, as a corollary of this, I can write down the length of the curve, right? Okay. Corollaries. Okay, L, I don't know, B of gamma will be equal to the integral from A to B to absolute values of gamma prime of t over apparently 1 minus gamma of t squared. Yes, gamma of t squared. And yeah, actually one can compute. So it is going to be 1 minus the absolute value of gamma t squared dt. This is the first corollary. The second important corollary, geodesics in the Riemannian manifold B2 GB are the following guys. Either the diameters passing through definitely through the origin, or also semicircle arcs orthogonal to the boundary, right? Or just circle arcs orthogonal to the boundary. This is because this is our transformation is inversion. So we know that who are geodesics in this model, either vertical lines or guys orthogonal to the boundary. And obviously, all these are the so-called generalized lines or generalized circles. They're like generalized circles orthogonal to the boundary, since the boundary line is mapped to the boundary of the unit disk. Then the generalized circles that were orthogonal to the boundary will be mapped to generalized circles orthogonal to the image of the boundary, which is also the boundary of the disk. And this eventually gives you only those options, right? Since vertical, well, these diameters are kind of generalized circles orthogonal to the boundary of B2, right? And these circles are just orthogonal, yeah. So these are our geodesics here. Again, since the metric tensor is also scaled, is the Euclidean one scaled. We also have, it is a conformal module, so hyperbolic angles are equal to the Euclidean angles in this model. Corollary number 4. In the triangle, in any hyperbolic triangle, with angles alpha, beta, gamma, we have alpha plus beta plus gamma is less than pi. Why? Since one can move any triangle to the origin, and then notice that the sum of angles in this triangle, say it is alpha, beta, gamma, alpha plus beta plus gamma is less than, what is less than, and then take a Euclidean line. So take a Euclidean line passing through these vertices. And note that alpha plus beta plus gamma is less than alpha plus beta prime plus gamma prime. This is a Euclidean triangle, and thus it is equal to pi, right? Corollary number 5. I want to finish with our primary goal. So corollary number 5, I will write it somewhere here. O is the origin, and P is any point. So O, P belong to B2. Then the hyperbolic distance rho sub B between O and P. And also let it be the geodesic gamma. You can parameterize it as the parameter T multiplied by P, right? So one can take gamma of T is TP. So gamma is the map from 0 to 1 to B2, right? Is a geodesic. One can compute that Blick's length on the segment 0, 1 is equal to, okay, it is equal to two inverted hyperbolic tangents. So it is 2 multiplied by inverse, right? The hyperbolic tangents, inverse of the Euclidean norm of the point P. Well, I suggest just to write down this integral and then use the fact that, so hint is in the fact that the derivative of this function, so that the derivative of this function is 1 over 1 minus x squared. And this thing will appear under this integral, okay? Well, you will also need to use the substitution, I guess, but yeah. Okay, this is very important. Corollary number 5, in particular, implies the following. Corollary 5 implies that hyperbolic circle is precisely implies that this corollary number 6 that hyperbolic circle centered at O is a Euclidean circle. As a consequence, the isometry group of H2, moreover, its stabilizer of O, it should be, well, yeah, right? We need to preserve this value, so that we need to preserve the norm of P. That's why it is the Euclidean circle. So, okay, I should write any the hyperbolic circle, okay, a hyperbolic circle, since I actually choose a hyperbolic circle centered at O, at the origin is a Euclidean circle centered at O. And with radius, the norm of O, yeah. And the stabilizer H2 of the isometry group of H2 of this point O is isomorphic to just the isometry group of the Euclidean circle, right? And this is definitely the orthogonal group of order 2. And one can also say the same about the isometry group of H2. And which is orientation preserving isometry group. So we have here SO2R. And finally, this is our corollary. Finally, we prove this theorem that the isometry group of H2 precisely, so well, the orientation preserving isometry group is precisely PSL2R, and the isometry group, the full isometry group of H2 is the semi-direct product. I will discuss a bit more this next time. Yeah, we didn't have enough time to start general hyperbolic, like general dimensions, higher dimensional hyperbolic models, but we will. And again, why this is true? We proved in previous lectures that the stabilizer of PSL2R of some point is equal to O2 or to SO2, right? But we didn't prove that the stabilizer of the full orientation preserving isometry group is the same. But once we prove it, and we proved it using this model, we are done. Since, right, our problem was that we showed that PSL2R is the subgroup G plus, right? But we wanted to show that they coincide. But we used the fact that since the stabilizer, right, the stabilizer is equal to, is isomorphic to G plus, then it coincides that, well, it implies that PSL2R is isomorphic to G. Okay? This is because of the fact that you can move, right? Any F can be decomposed, right? Any F is decomposed as, so any f from isom H2 is decomposed as the composition of some, I don't know, isometry. How should I denote it? Okay, let me write it f small, any isometry H, and G. Okay, not good. Okay, and S, where H belongs to PSL to R, and S is SO to R. That's the proof. So this implies that since both of them sit, right? Well, S is like the stabilizer, GO, right? So I am taking any element from my isometry group of H2 and decompose it into the product of some nice PSL to R, say mapping any point a point I to some point Z, and then I'm finding stabilizer. Once I prove that GO coincides with SO2, this means that it also sits in PSL to R. But then it implies that actually this isometry F is an element of the PSL to R, right? Sorry, I forgot to write down here isom plus. And the fact that the stabilizer here, right, the stabilizer, the element S sitting in the stabilizer here gives me the SO to R, but not something bigger, is crucial for proving that actually this group coincide, right? These groups coincide. That's what we used. Okay, so yeah, next time we will discuss probably the second model. I guess we will also talk about triangles, maybe some other metric relations in hyperbolic plane, and other models. That's the plan for the next week. Okay, thanks.